Okay, maybe. We'll have it here. There we go. Okay.
Brilliant. So for the second talk of the session, let me invite William Bauman, who will tell us how to grow a proof assistant.
Thank you. So let me tell you about a problem I have when I do my proofs. When I do proofs, I use a lot of notation. Much of it is domain-specific notation, like BNF grammars. Some of it is this sort of informal notation, user-defined notation, you could think of it as. And, of course, I have my notation that requires very serious, rigorous correctness criteria. So, much of it is very domain-specific. So things like BNF grammars, which I can use to very tersely define a formal system. And there are other ways I could define this system. I could describe it in English, I could use algebra, or I could use set notation. But we as a community have sort of settled on BNF grammars, and we know when we see a BNF grammar how to parse them very quickly, and we sort of understand them as a community, and they very tersely get to the point of what is the syntax of this language. Some of the notation I use is very informal, very intuitive. So for instance, when I define syntactic sugar, I can just say, oh, let this let expression stand for this application. And again, we as a community know what this means, and we understand it doesn't need any further specification. And then, of course, some of my notation, like when I write theorems, must be both very formal, because I need to know it's correct, but also very intuitive, so that I know what this theorem means, that I know that I've proved something meaningful. And the problem is, I wish I did proofs a little more like when I write my programs, so that I can write down all of this notation, but then have the computer check me. That way, if I do something silly, like I forget to define the syntactic category I, the computer could tell me. Or if I write down some syntax sugar, it could warn me if I'm doing something stupid, like I forget to use this E1 in the output. And of course, when I do my proofs, I could get errors when I forget to prove some corner case. And now, the way I don't want to do my proofs is take my nice standard, got a little bit of lag here. Take my nice standard familiar notation and then hand compile it into this assembly language of math. This is not how I want to do proofs. This makes it harder for me to communicate my formal system and harder to even write it. Now there are some existing solutions in modern proof assistants. So we have things like OUGHT, which will let me type up a BNF grammar and inference rules and that sort of thing, and then generate code in various proof assistants. We have notation and mix-fix systems and different proof assistants that give you the ability to define certain kinds of notation. We have parser extensions and OCaml plugins for Coq that allow you to get more sophisticated notation. But to accomplish my goals with all of this both mix of formal and informal notation simultaneously, I need many of these systems. And I keep finding myself wondering if there's a better way to design a proof assistant that will support the kinds of notation I use on paper. So, thinking about the way we design a proof assistant, we normally start with a core language, and then maybe we'll do things like add a surface language. And maybe on top of that surface language, we'll add a notation system for user-defined notation. Maybe we'll add a plugin system so we can start doing things like defining tactics. And then we'll expose a bit of all of these to the user. So this thin red line here represents all of the parts we expose to the user for defining new notation and new extensions. So what if instead of this design, we start from a core language, and then we build one single general purpose extension system that will allow the user to build all of these other systems as basically notation on top of the core language. So after we have this extension system, then we can define in user level code a surface language, a notation system, a tactic system, and maybe we'll have the ability to support more sophisticated things like BNF grammars. And the advantage of starting from this system would be we have one all-powerful system. Instead of exposing all four of these systems to the user, we just have one system that the user can learn. And it gives us a sort of a way of letting the user reuse the entire compiler front end. So they have all of the tools they need to start building more domain-specific notation. So that's what this, oh, okay. Forgot to delete some animations. Okay, so that's the idea behind my prototype proof assistant called Cur. The proof assistant is is designed with one idea in mind, which is user-defined notation. So note that here I'm using notation a little bit loosely. Even the surface language is considered notation over the core language. So today my goal is to convince you to think hard about user-defined notation. And to do that, I'm going to show you the design of Cur, show you how you can use this design to implement some of the standard general purpose notation that we see, like surface language, notation systems, and tactics, and show you how we can even build up things like BNF grammars. And then I'll conclude with some thoughts about how we can reason about notation and notation extensions that the user might define. Okay, so the first part of Cur is going to be its core language. This is actually the least important part of the proof assistant. You could choose it's arbitrary what you choose here, and it's not critical to the design. So what I'm going to choose is TT, which is a very similar core to Agda and Idris. And I'm just going to briefly show you this logic so you know what we're working with in the later sections. So in TT we have universes written univ I with some level I. We have an infinite hierarchy of cumulative universes, and we have one impredicative universe at the bottom. So we can think of this as set in the set hierarchy in Coq with an impredicative set. We also have inductive data definition, so we can define a new inductive type D of type T, with the first n arguments are parameters, and its constructor is declared by gamma. And then, of course, we have our term language, where we have functions. We have the dependent function type, so the result type of the function can depend on the argument. And then we have folds over inductive types, so we give one method for each constructor, and then we eliminate some E of type D. We do not have recursive functions, and there's no termination checker in this logic. Okay, so that's the core language. The next part of the system is, of course, the extension system. So this is going to be this general purpose extension system that's designed to extend everything in the language. We're going to use Racket, since Racket has been used to build things like typed Racket, PLT Redux, and Scribble. It's got a lot of language extension facilities that we can reuse, but this too is sort of an arbitrary choice. Here we could build a new extension system using OCaml or using template Haskell, but we're going to use Racket so we can reuse all of that infrastructure. So on the next couple of slides, I'm going to have code in two different languages. I'm going to use this blue color with this underlining to represent code in the object language, in the core language. And I'm going to use this red color that's not underlined to represent the meta language, all of the Racket functions. Okay, so for those of you who don't know, I'm going to go over metaprogramming with Racket. So this is how we write new extensions in the Racket system. We're going to begin each piece of code, each metaprogram with this begin for syntax, which just says we're no longer writing proof assistant code, we're writing an extension. The first part of each metaprogram in Racket, each of these extensions, is just a transformer, which is a function over object language programs. So it's going to take as input some representation of the core language. In Racket, this is called a syntax object, and it's going to return a syntax object. So this hash quote here is the data constructor for syntax objects. What this function does is it just pattern matches on the syntax object, and when it sees this ASCII lambda, a binding and a body, it's going to generate the Unicode version that we have in our core language. Okay, so the second part of each of these extensions is a syntactic hook in the object language. So we use define syntax to declare that this ASCII word is now a syntactic form in the language, whose interpretation is given by this transform lambda function in the meta language. So to get an idea of how these notations get elaborated, when we start running a program in this system, the first thing that's going to happen is elaboration. So we're going to get rid of all of the user-defined notation, then we'll call the type checker, and then we'll run. So when the elaborator starts running, it's going to keep track of this environment of keywords to their transformers, and when it detects one of these keywords, it's going to start up this compile time evaluator. It's going to ship the syntax object over to the compile time evaluator, and it's going to run at compile time our transformer. And that is going to produce a new syntax object that the elaborator is going to get back and start transforming. Okay, so that's the basics of metaprogramming with Racket. Now we're going to move to this other side of our little red line and take on the role of a user of this system. So we're going to start building up new notation. The first thing we're going to do is try to build up a surface language feature. Now recall that I'm using notation deliberately in a sort of loose way. So even surface language features are just notation over the core language. And we want to make sure that this system can will allow users to express even the sorts of things a language implementer might normally write. So the first thing we're going to write is a pattern matcher. So in our core language, recall that we only have folds over inductive types. So if we want to define the plus function, the first thing we have to write is, well, we're going to eliminate some natural number. We have to give a motive, which is this function that from whatever object we're eliminating, and it produces a return type. Then we have to give a method for each constructor. So if we get a 0, we'll return n2. If we get a successor, then we'll take in the x as an argument. We'll get a recursive function, recursive argument from the fold, and then we'll return s of that recursive argument, ih. And then we declare that we're folding over the object n1. So this is a really tedious way of writing anything. And you can see that most of the annotations in here are totally boilerplate that a compiler should be able to infer, right? So this nat annotation comes from the fact that we're eliminating n1, which has type nat. This annotation here is almost always going to be the same as this. This return type we can infer because in the base case we're returning a nat. This annotation on this recursive variable is always going to be the same as our return type. So wouldn't it be nice if we had some notation that just let us write match n1 if z return n2, if s of x return x plus n2. We're going to write this, and it's going to be all user level code. Okay, so let's see how we write this. So the first thing we do is we define some new syntax called match, and we're going to pattern match on the incoming syntax object and split it into the term we're pattern matching on, E, and into the pattern match clauses. Now we know that we're going to be generating this fold over an inductive type, so we're going to use this hash tick to create a new syntax object. And this hash comma here is just a way of escaping the syntax object and computing part of it. So we can imagine that hash tick and hash comma form a templating system for syntax objects. So we're going to say that we have some type D that we need to declare that we're folding over. We have some motive, and then we're going to take all of these clauses and turn them into methods. And then we're folding over this, this term E from the syntax of the match. To compute the motive, then we generate a new function where the type annotation is the same D that we're pattern matching on, and it returns some type R. For the type D, we can imagine that for a moment, and I'll come back to this shortly, that we have some function cur type infer that will just take this term that we're pattern matching on E and infer its type. To compute the return type, the first thing we need to do is parse all of these clauses and do things like annotate all the pattern variables and figure out how to transform those recursive function notations into a reference to that inductive variable. And so that will be a little bit more magic that I'll come back to. But once we've parsed all those clauses, then we can take that, then we can look over the branches and infer the result type. Okay, so the first thing that we need to do is add some way of inferring types. Now we could write our own type inference system as an extension, but it would be much easier for the users if we had an API into the core language, so that when an extension wants to do something as simple as just infer a type, we can just call into the core implementation and infer that type. So what we're going to do is add to our extension system this API function, cur type infer, which will force the elaborator to run, and then call into the type checker to infer a type on the core term. And now this is a very trivial kind of inference, since in our core language all terms are fully annotated. But it gives us the power of starting to build inference into some of our extensions. Now the second piece we need to do is we need to take all of these pattern matching clauses and turn them into these functions, these methods for the fold. So we need to infer the types on all of these pattern variables, and then figure out, the real hard part is to figure out how to turn this recursive function call into this reference to an inductive variable. So we actually need to identify what is a recursive function call and what's not. And the problem with this is we need to sort of reach outside the local syntactic tree of this match to do this. So it's not exactly obvious when we're just defining this function, but if we look at the abstract syntax tree, when we're defining this match, since we're defining notation, we're defining syntax, we only have access to this subtree here. But we need to actually reach outside of this subtree and detect, oh, we're under this definition of a plus, so this plus must be a recursive function call. To do this, we can first redefine what this define notation is. That means our extension system needs to support redefining existing syntax, and then we can use compile time state to communicate across these notation definitions. So what's going to happen in our definition of define is we're going to record the current function name as plus, so that when we get down into this match can look at the heap and learn this information about everything that happened earlier in the elaboration. So now when we're parsing these clauses, we just look at the current function name and we can detect these recursive functions and elaborate them into a reference to this inductive variable. Okay, so that's the first bit of extension incur. We can start defining surface language features. The next obvious target is tactics. So this is a much more general system than just little bits of surface syntax. This is going to require interpreting functions and maybe even doing I/O if we want to do interactive tactics. So let's see how we can do that using this design. So this is one way we could imagine using tactics incur. We need some syntactic form that says we're going to use tactics, and we've seen how to define that. We use define syntax to declare new syntactic forms. We need some way of declaring the goal. Now the problem here is our surface syntax can contain arbitrary user-defined syntax. So we need some way of taking this goal and reducing it down to the core forms, so that tactics don't have to consider arbitrary syntax. They can focus in on only the core forms. So we're going to need a little more support from our extension system to accomplish this. Okay, so what we're going to do is add another API call to our extension system called curexpand. And this is going to allow us to force the elaborator to run while we're elaborating other notation. So this is a way of just forcing the elaborator to run on a particular subterm during compile time. And this will let us do things like define a new solver, even if we have arbitrary syntax in the language. Once we run curexpand on it, it will eliminate all the new user-defined syntax and let us just focus on the core terms. And of course, we're still free to match on arbitrary syntax if we want by not using this function, but oftentimes we might want to just focus on the core language terms. Okay, so that lets us handle defining tactics just over the core language, even when we have arbitrary user-defined syntax. Now we need some way of actually representing tactics. And so there are a couple of options here. We can do something like define a new tactic DSL, LTAC style. We could define, we could go MTAC style and try to use cur functions themselves as tactics. Or we could do something in the LCF Hall VaryML style and use meta-language functions to represent tactics. But the best part of this whole design is that we don't really have to choose, right? Remember that we're in user-land code. Whatever we come up with, we need to make sure that the extension system will allow the user to define a whole other system. So what we actually do in cur right now, we have this NTAC system, is we use meta-language functions to represent our tactics, but we also add this support to the elaborator that allows us to force cur code to run at compile time. That way, if you have a meta-language function, you could easily implement the other two styles with this support from the extension system. And so let's just take a quick look at that function. We add one more function to our extension system, which will force the elaborator to run. It will then type check the expression, and if the expression type checks, it will run it at compile time. So we can do something like define a reflection tactic that will take a cur function and a goal, and then run it. It will generate this application and run it at compile time while the elaborator is running, returning a new function that can, returning a new function to the elaborator. Okay, so I started with this sort of grand vision of domain-specific notation, but so far all I've defined is surface language features and general purpose tactics that proof assistants already support. So let's see how we can go a little bit further and start defining sophisticated domain-specific notation like BNF grammars. So we've already seen how we define these new syntactic forms in the language. This is an example of how we define BNF grammars in Cur. So we have a few bells and whistles, like we can generate Coq code and LaTeX code. We can, since we have arbitrary arbitrary meta-language computation, we can just write these functions that will take the BNF grammars and output them into a different language while we're transforming them. And we can also do things like handle simple lexical binding by generating the De Bruyneized code. And the way we do this is when we define a new language, we can combine the language part and the syntactic class, and we're going to generate one inductive type for each of these syntactic categories. We're going to generate a constructor for each part of the BNF definition. So for instance, when we have this unit type, we're going to generate STLC unit, since STLC is the language, and this unit is the part of the BNF definition. And when the BNF definition contains references to metavariables, we're going to generate an argument to the constructor. And then while we're transforming this BNF grammar, we can, on the side, output to a new file the LaTeX definition. All right, so we have this small core, we have this extension system, everything else is just user-defined notation, but let me leave you with a few open questions. How do we know any of this notation is actually correct? And what does it even mean for it to be correct? And if we had those answers, we still have a lot of side effects in this design that we have to reason about. So for instance, in the pattern matching example, we use compile time state to change what even statically exists at runtime. We use, in the tactics example, we use reflection on syntax, which could break your parametric reasoning or break your referential transparency. And in the same tactic example, we have this sort of exotic control flow effect where we take something that looks like it might run at runtime and force it to run at compile time instead. So it's not even clear what stage something will run at from the syntax of the language. And then in our BNF example, we have binding manipulation. We're generating new binders that aren't syntactically apparent in the code. So I don't actually have the answers to how we reason about any of this, but if you have some ideas, we have a system you can experiment in. So let me leave you with a few takeaways. I think we need to make user-defined notation a priority. The way Cur does this is by starting from a single general purpose notation system that everything has to be implemented in. By doing this, we hope to better support domain-specific and user-defined notation, and we hope to give users the same tools and powers as normal compiler front-end implementers have. Thank you.
Thank you very much. Other questions?
I have one. So, do you have a good story for composing these extensions? If I write something that will give me lambda characters and give me the notation, everything, then I will, okay, I also want pattern matching, but it needs to interact suddenly with typing rules, with cases.
Right, so there's been a lot of work on this in languages in the Lisp style, like Racket. And in the very early slides, we had this example of the elaborator running. And the key part that sort of gives you this compositionality is that once a transformer generates some new syntax, it returns to the very start and begins elaborating. So if you have one piece of syntax or one piece of notation that generates notation using something else, so maybe you've taken STLC and then you've returned that from your pattern matcher, it will, after it's done elaborating the pattern matcher, it will return to the start and begin processing any new notation that's been generated. So there's a pretty good story of composing these hierarchically. The problem comes in when you have more of a diamond shape, where you have one library and two notations inherit from that, and you want to try to use both of them. And that still requires some user intervention in order to figure out how to compose those properly.
Okay, any more questions? Then I think let's thank the speaker again, and it's time for a break.
Thank you.